Okay, once you have a battery, the things you care the most is actually how much volt this battery can provide. In order to get that information, okay, we need to first learn these things called the standard reduction potential. Typically, it's going to have a notation of E naught. Again, the naught, like your G naught, means actually the standard condition. On the right, you can see a table. This table is the standard reduction potential of many atoms. The standard reduction potential is an intensive property. What it means, it's not going to be affected, okay, even you multiply a coefficient in front of the species. For example, here you can see F2 plus 2 electron, that give you 2F minus. Then your E naught is 2.87 volts. If today I multiply 2 in front of this, the E naught will be still the same. So these are actually the things that many students actually got messed up, because the standard reduction potential is an intensive property. So even you change the coefficient in front of it, it's not going to change the standard reduction potential. This is actually very different from when you calculate your delta G, delta H, delta S. For delta G, delta H, delta S, it is so-called the extensive properties. And for those properties, it will depending on the coefficient in front of your species. Pay close attention to this because so many students make this type of errors. Okay, so what does the standard reduction potential tell us? It actually tells us the potentials for this specific species to oxidize other atoms. The larger the E naught, the stronger the oxidant. If you see a larger standard reduction potential, it means they really like electrons. Because they like the electrons so much, they are going to strip electrons from other guys. Therefore, make themselves a very strong oxidant. In other words, if you look at these tables, if I ask you, is NaO4 minus in acidic solution a stronger oxidant than O2? So the way you solve this one is actually you first need to check out the standard reduction potential for your NaO4 minus in acidic solution. Okay, that means you must have the protons here. Its standard reduction potential is 1.68 volt. And the standard reduction potential for your O2 is only 1.23 volt. So it means this guy is a stronger oxidant than your O2. So make sure you have this concept. The larger the standard reduction potential, the stronger the oxidant. When you go back to this cell potentials, means we actually put two things together to form the electrochemical cell. How do you calculate the overall potentials of your cell? Typically, we call it E cell. This is the electrochemical cell notation you have. Here you can see the zinc becomes zinc 2 plus. The copper 2 plus become copper. For this part, it basically says copper 2 plus get 2 electrons that give you copper solid. This is actually a reduction reaction. So you can actually find out your E naught easily. Okay, so when you do this, you realize if copper 2 plus gain 2 electrons to form the copper solid, your E naught is 0.34. That's what's going to happen on your cathode. The zinc is going to become zinc 2 plus and gain 2 electrons. This is actually an oxidation reaction. So you are not going to find the standard reduction potential, okay? So how do you get the standard reduction potential? You actually need to flip this one first. So you want to look at for a species that undergo zinc 2 plus 2 electrons. they give you zinc. If you do these things carefully, you should see your zinc plus 2 electrons, they become zinc. So you can see lead E naught for less specific reduction is negative 0.76. So let's for this specific reduction reaction, right? But here, because what you have is actually oxidative reaction. So you need to actually flip this one. This will be 0.76. And when you have your cells, you actually adding these two things up. So your E cathode is 0.34. Your E anode will be actually 0.76. When you're adding up, you got 1.10 volts. Let's have one more example. Fe become Fe2 plus, Ag plus become Ag. Starting from your cathode, we know the Ag plus electrons, they give you Ag solid. So your E naught is going to equals to 0.8 volt. And then the other side is actually Fe become Fe2 plus 2 electrons. So into actually looking for the Fe2 plus 2 electrons. It's here. Okay. So it's negative 0.44, right? But since we flip the reaction, so you know your E naught for your anode is actually just 0.44. So your E cell is going to equals to your E naught cathode plus E naught anode equals to 0.8 plus 0.44. So your E cell will equals to 1.24 volt. Here is actually a couple more examples you can actually practice yourself. So using the same analogies from previous slide, I want to actually calculate this, and hopefully you can get the correct answer yourself. So here is actually questions that many of you is going to make mistake. And the reason is simply because I intentionally put a 2 in front of this species. So don't get confused, even though you see these coefficients. The standard reduction potential is the same because it is an intensive property. So once you see these reactions, you should actually be able to see this goes from positive 1. This is 0, right? This is 0. That's positive 2. The calcium go to calcium plus lost electrons, right? So let's actually our LoRa. So we know the LoRa is calcium become calcium 2 plus. And then for your copper, because it goes from positive 1 to 0, okay, that's our G rock. So copper 1 plus become copper solid. So we know that is actually our cathode. Therefore, from these two, you should be able to write the cell notation. Okay, we know you should always start from the anode. Calcium become calcium 2 plus solid aqueous. And then at the cathode is copper 1 plus becoming copper solid. In between, make sure you put your salt bridge. This will be your cell notation. Once you have your cell notations, then you can calculate your E cell. For the E cell, we know, start from your cathode, because we know it's copper plus 1 electrons, that give you copper solid. So your E naught is going to equals to, okay, so I need to go back and find out the numbers. So your copper 1 plus is 0.52. Okay, so this will equals to 0.52. For your anode will be calcium become calcium 2 plus 2 electrons. To find my inner anode, I'm going to find out the standard reduction potential of my calcium 2 plus. So for the calcium 2 plus, it's negative 2.76. And because we flip the sign, so this will be plus 2.76. So your E cell will be just the sum of these two. So when you're adding up, you know your E cell is going to equals to 3.28. The things that students make mistake is actually when they calculate the E cells, they think, okay, I have a coefficient 2 here, coefficient 2 here. I need to put 2 here, 2 here, 4 electrons. So I need to multiply by 2. So that is totally wrong because your standard reduction potential is an intensive property. So don't do this, okay? So I want to actually go through 2 more examples that apply the concept of the standard reduction potential. Example number 1. Is an acidified permanganate solution a more powerful oxidizing agent than acidified dichromic solution? So here you want to be careful because you see these things acidified. That means in the reduction reaction you're looking at must contain H+. Permanganate solution is actually MnO4 minus. Dichromic solution is actually Cr2O7 2 minus. So you need to actually find out the standard reduction potentials equation that contains these two. Who has a larger standard reduction potential, then will be actually a more powerful oxidizing agent. So let's go back to the table we have. If you look carefully, you will realize that there is actually one permanganate. There's actually another one. There's actually another one. There are actually multiple permanganates here. But from the question you know, the one you want to use must also have H plus inside the equation. So that means this is actually another one you should use. So you know the potential you're going to use is either 1.68 or 1.51 for your permanganate. The other species you want to look into is actually the dichromate. Dichromate is Cr2O72 minus. This is where your dichromate is. And then it has to be in the acidified solution. So you must see the protons here. If you check out its standard reduction potential, is only 1.33. In other words, in the acidified solution, your NNO4 minus, because they have larger standard reduction potential, they are actually stronger oxidants than your Cr2O72 minus. So to answer these questions, okay, what we're going to say is actually the E naught of your NNO4 minus is actually larger than the E naught of your Cr2O72 minus. Therefore, NNO4 minus is a more powerful oxidant than the Cr2O72 minus. The second question, can the KNO4, okay, the aqueous KNO4 be used to oxidize Fe2 plus to Fe3 plus under standard condition in acidic solution? Okay, so what you should do is actually you check out the reduction potential of your KNO4 in the acidic solution. So it's KNO4 at the same time you must also see the H plus. Okay, it's just 1.51. To oxidize ion 2 to ion 3, okay, you actually don't have the ion 2 to ion 3 because that's actually oxidation process, right? What you have is actually ion 3 to ion 2. So you can check out the reduction potential of ion 3 to ion 2, which is actually here. So ion 2 to ion 3, okay, we know will be actually negative 0.77. Since you only need 0.77 volt, okay, to promote this to happen. For your KNO4, it can actually provide 1.5 volt. So the answer to this question will be yes, it will happen because this provides a larger voltage than the need to promote less specific reaction.